In lesson number 9, we're going to be learning about something called the mean value theorem. And as we discover the mean value theorem, we're going to also talk about the intermediate value theorem. So those are two things that we're going to touch on in this topic, is the intermediate value theorem, also known as the IVT, and then the mean value theorem, also known as the MVT. Okay, just so you know, I am accessing the notes and simply working you through the notes and the examples. So you can click here and you can look at the same notes yourself. All right, so let's go ahead and get started. All right, so what exactly is the mean value theorem? What are its preconditions? What are some of its implications? Basically, let's think about it as a picture first off. All right, so let's talk about this picture here. Let's talk about a visual, and then we'll talk about how are other ways that you can actually look at the theorem. So let's suppose that we began by making a curve, and you can see that curve that is in red. And that curve, notice, is going through the point A. So call this over here the function at, or should I make it lowercase a? So that's the function at A. And then notice that there is another point on the curve over here, and you can call that the function at B. And so what happens is if you were to make a line between A and B, right? So you see this line over here that's called the secant line. If you were to make a line that's going through the points A and B, the name of that line is called a secant line because it's going through two distinct points. So that's why we call it a secant line. And so you'll notice that the secant line has a particular slope, right? It has a slope, and we've learned to take this slope before. In fact, this is what we called the average rate of change. So the average rate of change is essentially finding the slope of that secant line. And so how did that used to go? F of B minus f of A. Now where are we getting this from? It's really the slope formula, change in the y's over the change in the x's, because this point right here is a comma f of A, and this point right here is b comma f of B. So we're simply finding a slope using the slope formula as we've always learned it, y2 minus y1 over x2 minus x1. The only big difference, and we have been doing this since pre-calculus, so the only big difference you realize is instead of calling things x's and y's, we call them, the letter and then the function at that particular letter. Okay, now moving forward, what we're going to be talking about next, so notice how this is essentially pre-calculus, right? This is pre-calculus stuff. So how does this tie in with what we're learning now? So in calculus, we learned about the idea of a derivative, right? We learned about a derivative. And what you learn is a derivative is essentially the slope, but not of a secant line, rather a tangent line. So in fact, we had a lesson where we would keep saying this. We would keep saying the derivative of the curve is equal to the slope of the tangent line. And then we would make various connections. Well, what happens is you're moving along this curve, right? You're moving along this curve, and you're trying to create such a tangent line. So you need to make sure that the tangent line only touches at one point, right? Only at one point, not at 2 points, but at one point. You're trying to find some point on this curve, the red curve, such that when you make a tangent line there, it'll have the same slope, as the secant line. So let me repeat that. You're trying to find some point on this curve so that when you make a tangent line there, that tangent line will have the same slope as this secant line. So let's just pick a few points. I know that the end result is shown to you, but let me just show you some of the thoughts that might be crossing your mind and how it's a pretty normal thing. Let's suppose you made a tangent line right over here. Okay, remember, a tangent line means it only touches the curve at one point. So this is roughly a tangent line. But notice that the derivative of this tangent line, i.e. the slope of this tangent line, is not the same as the slope of the secant line. And so therefore, it's not what we're really looking for. What are we really looking for? We're looking for that one or multiple points on the curve where the line would have the same slope as the secant line. And so when we keep looking, we find that that would actually occur right there. So now what if you ask yourself, okay, now we have a tangent line and we have a secant line and they have exactly the same slopes. But how do you find the slope of this tangent line, right? And so this is what takes us back to lesson number 3, where we discovered that the slope of a tangent line is equal to the derivative of the curve there. So if you can find the derivative of the curve right at this point, you will have also found the slope of the tangent line there. And so how do you say that as far as our writing is concerned? Well, you can say the instantaneous rate of change is equal to f derivative. And because we need to refer to it with some specific point, we'll call that point C, where this actually occurs for us, where we finally find a point that works for us. So this is C. All right, this is the point C, and then technically that's C comma f of C. All right, and so how do we communicate that? We say that the derivative at the point C is equal to the slope of the secant line at that point C. Okay, so what we have created here, and again, this is the calculus end of it, what we have created here is actually known as the famous mean value theorem. All right, it's called the mean value theorem, and it is pretty much asked about every year on the AP exam. Okay, now what I'm going to do here is I'm going to pause, and I'm going to show you a different way of looking at it. So what I have here is an app that essentially talks about the same thing. So I have a parabola, okay? I have a function of a parabola. And I can refresh this and it'll give me a different parabola every single time. And so I have a parabola here. And notice that on this parabola, I am going from -3 to +4. So -3 and then +4. And notice that they have matching y values, and if you're wondering how would you calculate those y values, just plug it into the function, and it'll tell you what the y value is there at -3 and +4. So when you make this line, that is called the secant line. So what will the theorem do for you? Well, it allows you to basically calculate the slope of the secant line, f of b minus f of a, divided by b minus a. In other words, 6 minus 2.5 divided by 4 minus -3. And so when everything is done and said, you are done. You have the answer 0.5. So you're saying that the slope of the secant line is 0.5. So what my app will do here for me is as soon as I click on this checkbox right here, it'll actually give me that special point on this curve where such a phenomenon occurs, right? So I'm going to go ahead and click this checkbox here. And notice that at exactly 0.5, ironically, at 0.5, if you were to connect a tangent line to this parabola, you will notice that in fact the tangent line has the same slope as the secant line. You see that? And so what is the special point here? The special point here is 0.5. Okay, let me pick another such a situation just to help you understand this a little better. So I'm going to refresh this and I'll type in something a little bit different. So x cubed minus x squared. Let's see if this will give us something. So I've got x cubed minus x squared, and I'll zoom in a little bit, all right, into the function. And let's suppose I'm interested from -1 to +1. So -1 to +1. So notice what happened is we created a secant line, so it's labeled right here, secant line. We created a secant line that is going through -1, -2, and 1, 0. All right, so that's my secant line. Well, again, if you wanted to find the slope of this secant line, you would simply do y2 minus y1 over x2 minus x1, which in, again, pre-calculus and calculus, we call it f of b minus f of a over b minus a. And when you find the slope of this line, you end up with +1 as an answer. So when I click this checkbox, it'll tell me where is that special point. Maybe you can even estimate it. Just start to think to yourself, where might there be a line that connects so that the slope of that line would be the same as the slope of this blue line right here. So when I press this, that special point is right over here, and that is at -0.33. So notice it says f derivative at -0.33 is equal to 1. So you're probably wondering, how would you be able to find that -0.33? And that is what we essentially spend the rest of the lesson on, is learning a systematic process by which to figure out what is this value of c. All right, so that value of c is what really matters to us. Okay, now before we proceed, I want for you to make sure that even if you are simply watching the video, to pull out a notebook and jot these 3 things down. These are central points of the mean value theorem. And you'll notice that every now and then I call it MVTD. It's because it's technically the mean value theorem for the derivatives, because we do have something else called the average value theorem, right? And that's technically for integrals. And basically it's something that you have learned before, right? So that's the idea of 1 over b minus a integration of f derivative x dx. Now, we have learned this at a separate point. I don't want to confuse you between average value theorem and mean value theorem. So this was learned in lesson number 14. Technically, you were supposed to learn this beforehand, and you're supposed to learn this after. But because of COVID, we've been stuck with learning something after and then something before. Okay. So number 1 realization that you want to have as soon as you think of mean value theorem is the fact that what happened here is the slope of the tangent line was actually equal to the slope of the secant line. Okay, so the AP exam has its own creative ways of testing if students understand what the mean value theorem really means. So the slope of the tangent line equals the slope of the secant line. Another way to look at it, as I showed you over here, is essentially the instantaneous rate of change, or if you think about it, that's really the slope of a tangent line, is the same thing as the average rate of change, which is essentially the same thing as the slope of a secant line. And finally, the third way that the AP exam has historically tested students on this idea is actually just the theorem itself as far as the formula is concerned. So a lot of students, when you tell them the mean value theorem, the first thing they'll do is they'll write this formula down. And I can understand how it's a very useful formula, but please understand that the practicality of that formula is in points number 1 and number 2. Now, before we move to the next slide, the one thing that needs to be said is when we learn the intermediate value theorem, the intermediate value theorem had a precondition. And the precondition of it, you are welcome to look back at when you learned this in the previous lesson. And if you haven't watched that previous lesson, please stop this video because it will not make an incredible lot of sense when we start making connections between them, and review the other video, right? So the precondition in the IVT is that the function needs to be continuous, right? There can be no breaks in the graph of a function, and then you can use the IVT. So the MVT also has a precondition, and the precondition of the MVT is not continuity, it's differentiability. You must be able to take a derivative on that interval, because if there's any point on that interval where you cannot take a derivative, then the MVT no longer holds. So you must always mention the precondition, and you have to say that because the function is differentiable, therefore the MVT says such and such. And I will show you that more in this lesson. How exactly do we communicate that idea? Okay, so this is just a summary of basically how these two theorems are similar and how they're apart, what I will do is after I go through a handful of examples about MVT, I'll come back and we'll review, so what is the difference between the IVT and the MVT and some of the implications that they have. So let's go ahead and begin with the first example here for the MVT. It says that you are given f of x is equal to x squared. So I want you to think about, even the graph of x squared is basically a parabola. And our job is to find that value of c on the interval 1 to 3. So we're only looking between 1 to 3, where the derivative is equal to 4, right? So the derivative is equal to 4. So the derivative at that point c is actually equal to 4. So I'm going to show you a very systematic process, right, to go about the mean value theorem. The first thing that we need to do is figure out which theorem are we supposed to use, because oftentimes students get confused as to, do you want me to use the IVT or the MVT, right? So here is how we can look at it. You will notice that you've been provided the equation of the function f. And you need to prove something about, this is the most important part, about its derivative. So you have a function and you need to say something about its derivative. That is why you need to use the MVT. Okay, that is the one clear way of telling if you have a function and you need to prove something about its derivative, you're going to need to go through the MVT. If you have a function and you need to prove something about the function, that is the IVT. Now, this can get kind of interesting sometimes. Let's suppose that you had the derivative and you had to prove something about the derivative. Well, guess what? Because the mode never changed, that's still IVT. Let's suppose that you had a derivative and you had to prove something about its derivative, meaning its second derivative. Now that would be MVT. So what I'm trying to explain to you here is every time the derivative process is involved, that is an MVT question. Whenever the derivative process is not involved, right? This is not a derivative process. That's just a derivative function, but that remains a derivative function. You're talking about what's happening in the middle of that derivative function. Same thing goes for function and function. Notice how we're still in the same mode, function mode, function mode. That's still the IVT. So basically, the moment that you switch modes is a good way to remember that you're supposed to use the MVT. Okay? So how did we switch modes here? They gave us the function, and they asked us something about the derivative and where that point exists. So we know that this is going to be using the MVT. And this step is very important. It often gets overlooked, and it's also the main reason why a lot of students get the answer incorrect, because the way the AP exam words these questions, it generally seems a bit ambiguous, and you can end up with an answer in either case, because the IVT, if you recall from the previous lesson, also uses A's and B's and F of A's and F of B's. So you want to be more specific as to which one am I supposed to use here. Okay, now step number 2. You need to state whether the function is differentiable on this given interval. And you cannot start until you don't mention this, okay? And as I mentioned to you right here in the note, this step is important. If the function was not differentiable, then automatically you have to stop doing that particular part of the problem using MVT, because the mean value theorem has a precondition. And if that precondition of differentiability isn't met, you just don't use the theorem at all. Just like as I told you in the previous lesson, the Pythagorean theorem has a precondition that it only works on right triangles. If you give me a triangle that's not a right triangle, I cannot use the Pythagorean theorem anymore. So the MVT is very similar. If you tell me something isn't differentiable, well then I can't use the MVT to begin with. So the problem is either going to be solved in a different way or it's not going to be solved at all. All right. Now, for the sake of the AP exam, you generally just, mention that, yeah, it's differentiable and then move on. But if, that's only if you can't figure it out. But otherwise, you should make sure that this is a differentiable function. Now, if you're wondering, how do you know it's differentiable? Well, this is what we talked about. This is a parabola, and a parabola does not have any corners or kinks or sharp turns or vertical tangents or discontinuities, none of it, right? So that's a perfectly good polynomial graph, so it is differentiable, right? Now, here is the most important step. What you do is you set the slope of the line equal to the slope of the the slope of the tangent line equal to the slope of the secant line, right? Now, that understanding is very useful because if you understand it this way, you're essentially saying the mean value theorem. So what is the slope of the tangent line? How do you find the slope of a tangent line? Well, remember, for a slope of a tangent, you take a derivative and you plug in the point that you need. So that's precisely what we do. We take a derivative of f of x, and the derivative of f of x is equal to 2x. And then into that 2x, you're going to plug a c into it. Remember, we don't know where this point C is, right? We got to figure that part out. So here is the slope of the tangent line. If you want to call it a derivative, that's perfectly fine. Now, where did I use that logic from? In lesson number 3, we learned that the slope of a tangent line is equal to the derivative of the curve. And in this lesson, I'm telling you that according to the mean value theorem, the slope of the tangent line is equal to the slope of the secant line. So what are the connections we're making here? What we essentially did is we said, well, if the slope of the tangent line is equal to the derivative of the curve, and the slope of the secant line and the tangent line is the same, well, essentially we can skip the middleman here, which is the tangent line, and we can say that the derivative of the curve is equal to the slope of the secant line. That's essentially what we're doing in this part of the step. Okay, so long story short, take a derivative and plug in the point C. Okay, now what do you do after that? Next thing that you do is you find, and again, this is in the same step, by the way. Okay, you're going to find the slope of the secant line. Now, how do you do something like that? Well, first thing that you do is you note down what is A. A is 1. Okay, they told you the interval, A is 1. And you find out what B is 3. So those are the endpoints of the interval. Then what you do is you find the f of A and you find the f of B. You see how this rings a bell? It's basically finding a slope of a secant line using y2 minus y1, but you know, the notations look slightly different. So f of B minus f of A means f of 3 minus f of 1, and then B minus A is simply 3 minus 1. Now, if you plug into the function x squared, right, not into its derivative, but into x squared, 1 squared is simply 1, and 3 squared is equal to 9. So f of B is 9, and f of A is 1. So that's where we end up with 9 minus 1. And when you divide that by 2, you end up with 4. So what are we essentially doing? We're applying the mean value theorem, where you take a derivative of the curve and you set it equal to the slope of the secant line. And when you do something like that, you end up with 2c is equal to 4. And once you're done with that and you solve it, you end up with that magical point, and that magical point is c equals 2. Now, what I generally do towards the end is I try to show to students a few things. Number one, how do you write that concluding statement? Okay, so the concluding statement needs to look like this. This is very important. If you're spending all that time understanding the mean value theorem, and then you don't know how to express it on the AP exam, they unfortunately do mark point off if you don't know how to state it. Okay, or if sometimes not for not knowing how to state it, but if you say a little too much or a little too less. Okay, so the first thing that needs to be stated, and it's very important, you must say that f is differentiable. Okay, you must say that the function is differentiable on that interval that was being talked about. And again, usually this is simply restating what they already told you, but you need to say it anyway. So then, because the precondition, this right here is the precondition. Because you were saying the precondition is met, now you can go ahead and express the mean value theorem. You say, therefore, by the mean value theorem, there is a value c in that interval 1 to 3 so that the derivative is equal to 4. Okay, that's the question that they had asked. And you conclude by saying that value is 2. Right? So you had already shown your work for it, and you're now expressing as a statement. And I would recommend that you just kind of sit down and write this statement a few times until it settles in for you and you're comfortable with, you know, not just writing the statement, but understanding what the statement actually stands for. But this is a pretty general and acceptable level of writing on the AP exam, right? So a student who's going to get a 5 on this type of question is, you know, they're able to write this quite well. All right, now I want to show you a graph. I think it's very important to be able to accept what's happening here as opposed to just being like, okay, fine, I found a value of c equals 2, you know, so what? So basically here is my parabola. All right, so take a look at my parabola. And that parabola again is f of x is equal to x squared. Now what did I do? They were interested in the points 1, comma 3, so I went to 1 right over here. And I went to 3 right over there. You will notice that that's 3 comma 9 and that's 1 comma 1. So again, if you just were in a basic math class and you had to find the slope of a line, that's not that hard to do. So the slope of this purple line right here was equal to 2. And so what you did is you took a derivative of the curve, and you set it equal to, what did I say 2? Sorry about that. That's actually supposed to be 9 minus 1 is 8 divided by 4. So you took a derivative of the curve and set it equal to 4. And what you did by doing something like that is you found that point x where such a thing occurs. And it turns out that happens when x is equal to 2. So if you're wondering what is it all about, it's all about you figuring out what is that value where you would connect a tangent line and it would have the same slope. So here is my tangent line, and its slope is now also equal to 2, guaranteed, because notice that these two are actually parallel to one another. All right. So as we continue, we're going to keep talking about, you know, similar ideas. But here is something for you. It says, explain why there must be a value r. Okay, so they're saying explain why there must be a value r for r is a number between 1 and 3, such that f of r is equal to 7. Now let's pause here. Do we use the MVT or the IVT? Okay, so we were given a function. This is what we were given. And now, instead of asking us about the derivative, they're saying talk about f of r being equal to 7. You get that? So they're not asking us to take a derivative. There is no derivative process involved here. It's the same mode that they're referring to. They gave us a function and they're asking us about a function being equal to 7. In other words, this, even though it's in the lesson for MVT, and I do this on purpose, even though it's in the lesson for MVT, what we really need to use is the IVT. Now, again, if you're wondering how do you use the IVT, this is why you need to stop this video, and in case you haven't watched the previous one, you have to watch the previous one to understand what the IVT is saying. All right, but as I go through it, I'll try to remind you of a few things about the IVT. Okay, now, we have done step number 1. We have determined which one of the theorems we need to use. Okay, we know that we need to use the IVT, and basically we've been given a function and it wants us to prove something about the function and not its derivative. So IVT. Okay, now you need to begin by writing the precondition for the IVT. Now, as I started this lesson, I talked about this and I'll mention it again, is it's got to be continuous. So you got to ask yourself, is f of x is equal to x squared continuous? Well, in the previous example, it was differentiable, and we have learned that if something is differentiable, it's automatically also continuous. And an important note to make here is, let's just suppose it wasn't continuous. For some hypothetical reason, it wasn't continuous. Well, then you couldn't use the IVT anyway. It would be over. You would just say, I can't use that theorem. Okay, so we state that, all right, we know that f of x is equal to x squared is continuous, and so then we are done with step 2 and we move over to step 3. So notice how step 1 and step 2 isn't necessarily doing any actual writing or work. It's just you glancing at the function and making sure that you're using the proper theorem, and then accordingly you're using the proper precondition. So the IVT uses the condition of continuity, whereas the MVT uses the precondition of differentiability. Okay, now how do we go about this? It is quite similar to how we go about the MVT, except we're not finding any slopes here. There is no reason to find any slopes because a slope would imply that we're taking a derivative process. We're doing nothing of the sort. So now we're going to go ahead and find the A, and again the A was equal to 1, and the B, which is equal to 3. And then we will find the f of A, and we will find the f of B. So that would be the f of 1 and the f of 3. Now notice how, again, this is very similar to how we started off with the MVT, right? So we find out that we have basically 1, 1 and 3, 9, right? Now, notice that the number 7, so let's talk about the problem itself. It was saying prove that the function is ever equal to the number 7. Now, I want you to think, if the y value at 1 was 1, and the y value at 3 was 9, right? The theorem is all about thinking, okay? Do you realize is the number 7, because that's the one they're interested in, is actually between. It is an intermediary of 1 and 9. And so once you have discovered that, how do you write a concluding statement? And in a little bit, I'll talk about what does it mean. So here's what you begin by writing down. Okay, here's what you begin by writing down. Right, we're done with the problem. That's all you have to do. But to write it down is very important. So you begin by saying that since f is differentiable on this interval, it is also continuous on the interval. And it is important that you mention continuity this time because of the fact that you're using the IVT. So you want to tell them that, look, you told me already that it's differentiable, so it's implied that it's also going to be continuous. Okay, now how do you write this? I know that it's going to seem rather awkward, so I'm going to be utilizing the colors, and again, the colors are already written for you, but I will point to them so you understand where I got what piece from. And similar to the mean value theorem, this is quite generic. If you are struggling to agree with it, that's separate, honestly, but you can still get all the points for this question on the AP exam because if you can understand the structure in which you write this, you're in perfectly good condition to get the question correct. Okay, so I begin by saying that f is differentiable on this interval, and therefore it's also continuous. Now, what have I established here? I have established the precondition for the IVT. That's why that first statement is important. Now, how do you conclude this? You do not talk about any slopes once again, right? What do? You say that the number 7 is between the f of 1 and the f of 3. Okay, so the number 7 is between the function value at 1 and the function value at 3. But the question is, what was the function value at 1? The function value at 1 was 1. So what you do is you write down this little notation here. You say that 1 is equal to f of 1, right? And then on the other side, you write down that because 3 corresponded to 9, that the f of 3 is equal to 9. So what you're saying is the number 7 is between the number 1 and the number 9. With these inequalities that you've made here, that's getting that statement across. And so you say that since this is true, since this is actually true, the IVT guarantees, okay, it has a guarantee now, that there is going to be some value in the interval 1 to 3 such that the y value would actually equal 7. Okay, now you're probably wondering, I thought the value itself was 7. No, we're saying that there is some point on the x-axis, all right, there's some point on the x-axis named r, where when you find the y value of that, you'll find that that's actually equal to 7. That's what we're implying. Now, if you're wondering, well, can we find that? No, not necessarily the whole point of this exercise. The point of this exercise is to make a statement that the IVT works and what that might actually be. But I took the trouble of making a graph for you, and just so you are more convinced of this, And so let's take a look at this graph here. Okay, so this graph has f of x is equal to x squared, and that would be this parabola. And what I did is I made a dashed line at f of 1, and I made a dashed line at f of 3. I want you to think of this like the out of bounds line, okay? So notice that between the f of 1, which is 1, and the f of 3, which is 9, the number 7 does drop in between that interval. So the number 7 works for us. But what I did is just to talk about that point R, because a lot of students, they're able to get this question somewhat correct, but they don't understand what the theorem was saying, right? So the theorem was saying that there is some number, and here is that number, 2.646, where, so this is R, okay? This is the value of R, where the f of R is actually equal to 7, right? And the IVT did not tell you what the number is, it just guaranteed you that such a number actually occurs. All right. So I have several such examples, and what I generally do is after doing the first example in such lengthy detail, I ask my students to take the moment and try the next example by themselves. Okay, so if you want to pause the video right now and try example 2A and example 2B, it would really help you to start developing this idea as to how do you, which theorem do you use and how do you actually use the theorem. All right, so as I go through this example, it'll be a little bit quicker because we now know a systematic process of going about it. So let's read the question really quickly. It says that you're given f of x, so you're given a function, all right? That's the first thing to note down is you're given the function, and this is a polynomial function, so you know it's going to be differentiable, you know it's going to be continuous. And then you are given an interval, so the interval definitely matters. Okay, so -2 to 2, and again, what that means is this is going to be RA, and this is going to be RB. So A is -2, B is 2, and then they're asking you to talk about that point C, or give them that point C where the derivative is equal to -8. Now, what you should realize is if they gave us a function and asked about a derivative, that is the mean value theorem, right? So that takes care of step number 1, because step number 1 says first make sure that you're using the correct theorem. Step number 2 says, well, is it differentiable? And we know that because x cubed minus 12x is a polynomial function, there's basically nothing that would cause it to become undefined. And so it is differentiable, all right? It's not going to have any issues or any problems on the interval that they're interested in, which is from -2 to 2. All right, so now let's get to the actual application of the mean value theorem. All right, what did we discover? The first thing that you do is you take a slope of the tangent line. Now, how do you find the slope of the tangent line? You take a derivative of x cubed minus 12x. So the derivative of x cubed minus 12x, we all know, is 3x squared minus 12. And you plug in c. Now, a lot of students ask, do I really need to plug in c? I forgot to plug in c. No, the AP exam won't really hold you that stringently to it. But technically speaking, because you're implying that there is some point c that exists like that, it would be most appropriate to plug in c and say that instead of 3x squared minus 12, it's 3c squared minus 12. Okay, now comes the slope of the secant line. How do you find the slope of the secant line? You basically know what a and b were, all right? You know that a was -2 and b was +2, and your job is to go back to the function. Be careful, not the derivative, not the derivative, okay? Not here. You go to the original function over here, and you plug in -2 and +2. Now, when you plug in -2, it so happens that you end up with 16. And when you plug in +2, it so happens that you end up with -16, right? And so when you actually calculate everything, you end up with a slope of a secant line as -8. Be careful, it's not 0, but it's actually equal to -8. So what I've done here is I've colored them for you, one in blue and one in purple. The idea is for you to take the blue and set it equal to the purple and solve it. Okay, so realize that the only step that you're really actually doing work is step number 3. right? So even if you're in doubt and you just remember this formula right here, you should be in shape to at least get a part of that point. Although it's not impossible to get the second point, but you need to be able to write that particular statement. Anywho, so we set 3 squared minus 3c squared minus 12 equal to negative 8, and when we solve it, right, when we do the algebra there, that becomes 3c squared is equal to positive 4, and then when you divide, you end up with 4/3, and you take a square root, you end up with 4 over 3 square root, which can simplify a little bit to 2, but with still a square root of 3. So don't worry about rationalizing and stuff like that. But when you calculate this, you end up with negative 1.155 and positive 1.155. And one neat thing to note is, notice how in the interval negative 2 to 2, this number, negative 1.155 and positive 1.155, these numbers are within the interval. So these are both points, let's call them C1 and C2, that actually fulfill the mean value theorem. Now, how do I write this as a concluding statement really quickly? I say that, number one, the precondition is met. Remember, this is a precondition. We know that f is differentiable on negative 2 to 2, okay? And therefore, we know that there must be a value c in that interval so that the derivative is equal to negative 8. And then we conclude by saying that these values are positive and negative 1.155. Now remember, we got these values in step 3, so that just stating it is, not sufficient. You have to show them where you got that from. But I would imagine that's the easier part for many students to do, and to write about what they did is usually what gets them into a bit of a fix. Okay, really quickly as a picture, if you take a look at the lines that I've drawn for you here, the purple line is the secant line, right? That's the secant line, and so it has a slope that is equal to, what was it? Negative 8. Right? And so you're looking for where you can connect tangent lines that would have the same slope, meaning they're parallel, right? The tangent line and the secant line are parallel to one another. And so those 2 points are essentially what you solve for, okay? And those points are right here and right here. And so why do we call it negative 1.155? Because on the x-axis, that's what it matches up with. And this one is positive 1.155. Now, for some reason, if you need the y value, that's totally okay. You can plug these back into the function, all right? So the function, whatever it may be, if it was x cubed minus x squared, was it something like that? You can go, or sorry, x cubed minus 12x, right? I don't want to mistake that. X cubed minus 12x, you can plug in positive 1.155, and then it'll tell you what that matching y value is, okay? So just in case you need it. And usually they don't ask for the y value as well. They usually just ask for the value of c. And again, moral of the story, these are the values of c that are so special because that's where you connect a tangent line and it's got the same slope as that of the purple secant line. Okay, so you can again pause this video and you can solve the next question. So basically this question says, can you tell us if there's a value of r where f of r is equal to 10? Now, again, what did we have that was given to us? The function. What are they asking us for? The function at some point. Meaning, you know that this is going to be a process of IVT because they're asking you about the same function that they just gave to you. So you just need to basically prove that this function goes through 10. That's all it is. And so how do you go about it is usually the question that most students ask. Okay, so step number 1 we are done with. We know this is the IVT. Step number 2, you must check the precondition. And because, again, in the previous example, 2a, we noticed that this is a polynomial graph. Well, obviously, if it's a polynomial graph, it must be also continuous. So we're good on that front. And we continue to step number 3, which is the most important step. So I show that the f of negative 2 is equal to 16, and the f of 2 is equal to negative 16. And then after that, I notice, right, just using this very practically, notice how 10, because they were talking about the number 10, notice how the number 10, it does fall in the interval -16 to +16. The number +10 is in that interval, right? So you know this actually occurs. So you're really just done with the problem. But again, what really bothers students is to be able to summarize it and get those full points. Okay, so how do you summarize this? Here goes again. First thing that I do is I state the precondition. All right, I say f is differentiable on the interval -2 to 2, and therefore it's also continuous. Precondition met. Okay, now, because they were interested in the number 10, and I want to say that the number 10 does fall within the y values of -2 and +2, I write that in, and then I show them that the y value at 2 is -16, and the y value at -2 is equal to +16, right? And so it does fall within that interval. And not just that, the number 10 is greater than -16 and it is less than +16. So we conclude that the IVT guarantees that there is some value r in that interval where f of r is equal to 10. I know it's a mouthful, but try to get used to how it's being written. And now I want to take a moment and just kind of show you what this theorem really stands for and how useful it really is. So notice how uh, f of +2, right? F of +2 is equal to -16, and f of -2 is equal to +16, right? So here's -2, here's +2. And so we were interested in that interval from -2 to +2. And what we do discover is in that interval, within that interval, right over here, there is such a point, right? There is such a point where its y value is equal to 10. You see that? And so if you're wondering what is that point is called r, and that point happens to be -0.893. If you're wondering how did the calculator or the computer do this, it basically took the function and it set it equal to 10. Notice how in the mean value theorem you take the derivative and set it equal to the slope. Here you just take the function and set it equal to the y value. So it's interesting. You'll notice that there is another value that such a point occurs. There's a third value where such a point occurs, right? But these are not the values we are looking for. We're not interested in them. Yes, if they wanted to widen the interval, they would have said so. But they were specifically interested in only a value between -2 and +2, and we have proven that such a value exists, and it's right over here. So we can ignore the -2.93 and the 3.823, right? It's irrelevant to us because we've gotten the point across. In example 3a, we continue this process of checking if we're supposed to use the mean value theorem or if we're supposed to use the intermediate value theorem, and then we figure out what that value of c would be that will work in case the mean value theorem applies, or setting up simply a statement if the IVT applies. Now, in this question here, one thing that you'll notice is you're given the rational function. So already this is kind of unique because it's not a polynomial function, it is a rational function, and we know that in a rational function, it actually does have a vertical asymptote. If x is equal to 0, then you would have some issues with this function here. So in other words, it's undefined, it's not continuous when x is 0, and it's also therefore not differentiable when x is 0. In fact, I have a graph of it right here to prove it. So in a question like this, if they, let's suppose, asked you that on an interval -2 to 2, right? So here's -2, and here is +2. They ask you to tell if the derivative is ever equal to 1 over 4. We understand that given a function and them asking us for the derivative means that we have to work with the MVT. However, one thing that we notice is the MVT cannot be applied here. And the reason why the MVT cannot be applied is that this function is not differentiable when x is 0, right? So it's not differentiable there. And the theorem only works as long as the derivative can be taken everywhere on that interval. And so that is pretty much where the problem actually stops, right? We don't actually go any further with that. Yes, we do know that we're supposed to use the MVT, but as soon as we try to work with the MVT, that actually fails because of the lack of differentiability at x is equal to 0, right? So here is the vertical asymptote, right? Also known as an infinite discontinuity. And so that's all there is to that part of the question. Now, what if, on the other hand, they took the same exact function, right? In example 3b, what if we took the same exact function, and this time we took that function and we were asking about the interval 1 to 3? Well, in this situation, now it actually does make a difference. Because in the interval 1 to 3, notice that the number 0 falls outside of the interval, right? So it still is true that this function is not continuous or differentiable at 0, but the thing is, the interval that we've been given is from 1 to 3. In other words, the mean value theorem can now be applied, right? So you want to take a moment and pause the video and try out the process that we have discussed in the past couple of examples and make sure that you're able to find that value of c such that the derivative at c is equal to negative 1/3. All right, let's take a moment and just make sure that we're able to work with a question like this. So first off, we know in step number 1 that we're supposed to use the mean value theorem, so that's not really a big concern there. In step number 2, we know that it is still differentiable when it comes to the interval 1/3. Yes, we understand that that vertical asymptote still exists, but that's at x equals 0, and x equals 0 is not on the interval 1 to 3, as I said earlier. So step number 2 also checks out. All right, now step number 3 is the main step. All right, this is the one that you never forget, and this is the one where you actually do something, where you begin by taking a derivative of 1 over x and setting it equal to the slope of the secant line. So if it's been a while for you and you need to, again, practice how you take a derivative of 1 over x, the first thing you would do is you would rewrite it, and then the derivative would be negative x negative 2, which becomes negative 1 over x squared, like that, all right? So at the point c, here is your derivative, negative 1 over c squared. Now the slope of the secant line on the interval 1 to 3 would therefore be negative 1/3, right? And you can take a look at my work there. It was basically the f of 3 minus the f of 1 over 3 minus 1, and I eventually end up with negative 1/3. Remember, you take what you got between those two and you set them equal to one another, or you set them equal to one another. And when you set them equal to one another, this basically becomes a cross multiplication. Notice how the negatives basically cross one another out. And c squared is equal to 3, and therefore c is equal to plus or minus the square root of 3. Okay? And you'll also observe that that interval, 1 to 3, does contain one of these results, and 1.732, right, 1.732 falls within the interval. Now notice how the negative 1 does not end up in the interval, and that's perfectly fine. So we will not include the negative answer, and so the only value that really matters here is c is equal to positive 3. So as we conclude with this, we go ahead and we write down that number 1, we know that it's differentiable on 1 to 3, right? Again, on 1 to 3 it is differentiable. We know that it wasn't on negative 2 to 2. And then we conclude that by the mean value theorem, there is some value c between 1 to 3 such that the derivative is equal to 1/3. And that value, this is a small typo, right? You get rid of the negative, and that value would be 1.732. Really quickly, I have a graph for you just to convince you a little better. Here is 1, 1. Here is 3, 0.333, or basically 1/3. Those are your f of 1 and your f of 3. And notice that at 1.732, which does fall within the interval 1 to 3, there is a tangent line that has the same exact slope as the secant line. So they have the same slopes. And that's essentially what the MVT is trying to prove, is there is such a point C where the two lines would have the same exact slope. That's all there is to it. Now, in this next example, we're going to just briefly discuss a specialized case of the mean value theorem. Okay, so we've learned now the mean value theorem is where you essentially make sure that the function is differentiable on that interval, and then you set the slope of the tangent line equal to the slope of the secant line. And I wrote that as I said it. Okay, so slope of the tangent line equals the slope of the secant line. This is the best way to learn it. Just write it down a few times, say it to yourself, and it'll come through. So the special case of the mean value theorem, okay, and I've rarely seen the AP exam refer to this specifically, but it's good to know what the name is, right? So the name of this is called the Rolle's theorem. And in this special case, what happens is you find the slope of the secant line, and you discover that the slope of the secant line is actually 0. So this is the special case. Now, you could go about this just perfectly fine without knowing that this is a special case, by the way. So you find the slope of the secant line, you find out it's equal to 0, and then something interesting happens. And so this is what I wanted to discuss in this example. Number one, you've been given a function, right? So we are familiar with that. We've seen this in 3 examples now. And they are interested in a specific interval. And notice how this is a polynomial function, so it's perfectly differentiable on all values of x. And beyond that, they want you to prove that the derivative is equal to 0 at some point. So notice how they're taking a function, and then they're talking about its derivative. And so it makes sense that we're going to be using the mean value theorem, because they're asking you about a derivative of a function. So we use the MVT. Step number 2, we know that it is differentiable on this interval -3 to 4 because it's polynomial. So let's go to step number 3. In step number 3, what have we learned is you take the derivative of the curve, so 2c minus 1, and the slope of the line. Now when you go about to find the slope of the line, we understand that if the interval is -3 to 4, that's going to mean f of 3, f of 4, and then you subtract them as f of 4 minus f of -3, and then 4 minus -3. And when you do that, you discover that the f of 4 is 0, and the f of -3 is 0. And so 0 minus 0 is going to give you 0, right? And in the denominator, it's not 0, it's actually 7. 4 minus -3 is 7. But that doesn't really bother us much because 0 divided by 7 is going to give us 0. Okay? And so because the because the slope of the secant line we got was equal to 0, basically it's like the first derivative test. And this is why this theorem became so popular, is because it segues into what we spent several weeks on, which is the first derivative test. Because what was the derivative test? Basically take a derivative and set it equal to 0, because that's where your critical points lie. And so that's what's special about this sort of problem. And so you can solve 2c minus 1 equal to 0. You end up with c is equal to 1/2, and then you can make a valid conversion. So what we can say is the function is differentiable on the interval -3 to 4. And so by the mean value theorem, or more specifically, Rolle's theorem, we know that there is some value within that interval so that f derivative is equal to 0, and that value happens to be 1/2, or basically 0.5. So notice that the only difference is instead of saying MVT, I said Rolle's theorem. And the reason why it's Rolle's theorem is because this is a special case when that derivative is equal to 0. And even though we've learned the entire topic already, this was actually the basis of the derivative test. So notice that you have a secant line that is running from -3 all the way to 4. So this is our secant line. And notice that the slope of the secant line is also equal to 0. And our tangent line is over here. And our tangent line also is parallel to the secant line, i.e., it must have a slope of 0, right? So the whole process of taking a derivative, setting it equal to the slope of the secant line was to figure out what is this point where such occurs. And so that point is 0.5. All right, now what we're going to do is we're going to apply the same theorem, the mean value theorem. Remember, Rolle's theorem is just a special little case of it. But we go back to the general idea of the mean value theorem and the intermediate value theorem. And I will show you some popular AP questions that have come out of the MVT. And it is guaranteed to be asked about every single year. Okay? So let's go ahead and start. What we've been told is you have two functions that are differentiable. Now this is very important because if they're differentiable, what that means is you could technically use the MVT on it, or you can use the IVT. Because if it's the differentiable, the MVT qualifies. But we know that if something is differentiable, it's also continuous. And if something is continuous, then the IVT can also work on it, right? Now, we've been told that there's a function, and the equation of the function is h of x is equal to f of g of x minus 6. So you could say that h of x is really a composite function that's composed of f of g of x, and then it also has a subtract 6 on it. So the first question says, explain why there must be a value r so that in the interval 1 to 3, so we're only interested on the interval 1 to 3, that h of r is equal to -5. So I hope you've caught on to this, is if we've been given a function called h of x, and they are asking us about h of r, meaning r is some specific value, but what's important here is notice that these are both functions, right? These are both functions. We're going from function mode into the same function mode. And because it's the same function mode, you know that what really applies here is the intermediate value theorem. Now, getting into some of the specifics as to how AP structures these questions, whenever you see where it says, explain why there must be a value r, this should ring a bell for you that this is going to either be the MVT or the IVT. Okay, this is what you should think. And I just showed you that we would be using the IVT to work with it because it's telling you, it's giving you a function and it's asking you to prove something about the function itself. All right. Now, what is the requirement? What is the precondition? Remember, you always need to show this. The precondition is continuity. You need to show that this is continuous. Now, how do you show that something is continuous? It's a lot easier than you may think. All you need to say is the fact that f of g of x is a differentiable function because f and g are differentiable. And so therefore, the function h is also going to be differentiable, right? So h of x is also differentiable. Now, if h of x is differentiable, what is it automatically? It's also going to be continuous, right? So how exactly do we write that? We can write down, since f and g are differentiable, we know that h of x, which is equal to f of g of x minus 6, is also continuous on the interval. So look at these keywords here. I mentioned differentiability, and then I mentioned continuity, because anything that's differentiable is automatically also continuous. Okay, so what we're doing now is we're using the IVT. So if you need to go back and review, take a look at how the intermediate value theorem was utilized in these examples 2b and example 1b, and I showed you how we can use the IVT in both of them, right? And how do we express our answer. But the only work that you really need to do in the IVT is essentially figuring out what the function values are, okay? So the numbers that we're interested in are 1 to 3, right? So what we need to do is find the h of 1 and find the h of 3. So when we find the h of 1, we discover that the h of 1 is equal to 3, and we discover that the h of 3 is equal to -7, right? So the number that they were interested in specifically was the number -5. Now notice -5 is between -7 and 3. It's definitely, if there was a number line from -7 to 3, -5 would fall within the number line. And so what do we do at that stage to finish up our logic, right? To finish saying what we want to say, we write down that h is differentiable on 1 to 3 and therefore also continuous. Again, what is this part of the statement? This is the precondition, and you must write it, right? Now, why are we impressing on the fact that it's continuous is because we're about to call on the IVT, right? So now, we say that the number -5 is between -7 and 3. But the specific way we say it is we say h of 3 is equal to -7 and h of 1 is equal to 3, right? So, I mean, it's really just saying this right here. Please realize that. It's really just saying that, but it's saying it in a specific way. And I can assure you that even if you didn't say it in that specific way, as long as you get the idea across, then you'd still be in good shape. But it's always just better to have a general statement, some structure to go with as you're writing these final answers down. So you conclude that the IVT guarantees that there is a value r within that interval so that h of r is actually equal to -5. All right. Now, in 5b, what we're going to do is it's using the same exact pieces of information. It's giving you h of x, but the question, which is right over here, says explain why there must be a value of c within the same interval, 1 to 3, such that h derivative of c is equal to -5. So at this point, you should realize that because they are going from the function mode into the derivative function mode, that can only mean that we have to utilize the MVT. So we know that we need to use the MVT. Now, using the same logic as before, right? I know this is a bit repetitive, but using the same logic as before, we say since f and g are differentiable, we know that h of x is also differentiable on that same interval. All right, so we move on from that. Now, in the MVT, right, we don't need to show that a number falls between two other numbers. Instead, what we focus on is the following. We're going to take the slope of the tangent line. Now, the slope of the tangent line is right over here. And the slope of the secant line. Now, to find the slope of the secant line, what that means is you need to find the h of 3. And the h of 3 means you need to find the f of g of 3 and subtract 6 from it. You see that? Because here is the equation for h of x. It's f of g of x minus 6. So if we go to the table and we discover what is the g of 3, the g of 3 is 4. So the question becomes the f of 4 minus 6, like that. And so now we have to find the function at 4, which is equal to -1. So this becomes -1 minus 6, which gives you -7. And that's how I got this -7 over here, right? And then using the same logic, we find the h of 1, and the h of 1 is going to give us a 3, right? So once we have those two pieces of information, we go ahead and we subtract the 2 and divide by 2, and we end up with an answer of -5. And so what we're saying is the derivative, which is the slope of the tangent line, is equal to the average rate, which is the secant line, or its slope, sorry, which is equal to -5. So it's saying that, and I put a little note here for you. It says, notice how this question is not asking us to find the value of C. We didn't have to find the value of C. It just wanted us to prove that this actually works out, meaning this number is equal to that number. And we did that, right? So we're going to go ahead and write a concluding statement. Again, notice how I first established the precondition. All right, very important. We know that H is differentiable on 1 to 3. And therefore, by the mean value theorem, there is a value C where that C is between the interval 1 to 3, where H derivative is equal to H of 3 minus H of 1 divided by 3 minus 1, which is actually equal to -5. In example number 6, I'm going to show you a free response question that is oftentimes asked. And it really is asking for you to use the mean value theorem, all right? But it won't specifically say that. And so I'm going to help you kind of notice some of those indicators to understand where this comes from. All right, so in example number 6, you have a table of values. And this is something that we've discussed before, but in a different lesson. So notice that you have some times that are given to you, right? So this is, basically 0 through 6 minutes. And then you have a function called C of t that's measured in ounces. And we eventually will learn that that's really just the amount of coffee falling in through a coffee maker. And the number of ounces, notice, is basically increasing as we go along in this function here, right? So as the 6 minutes seem to be going by, the amount of coffee is also increasing. Very simple, right? Now, the next thing, what we'll do is we'll just kind of get oriented with what's written here. It says hot water is dripping through a coffee maker, filling a large cup with coffee. The amount of coffee in the cup at time t, so time t, and we know that this is measured in minutes, right? From 0 through 6 is given by the differentiable function. So now notice this is an important word for us now, right? Differentiable. What does that mean? That means we can use the MVT and we can use the IVT because differentiable also means continuous, right? So where t is measured in minutes, and so it says selected values of C of t measured in ounces. So C of t is measured in ounces are given in the table above, and we read the table a moment ago. So the question says, what does it mean? Now, this is not from the AP exam, but it just helps to understand the structure of these problems. It says, what does it mean that C of t is differentiable function? And is it necessary for it to be mentioned? So what we understand is if something is differentiable, you can find a derivative there, right? Or you can find how fast that coffee is dripping through the coffee maker, right? That's what differentiable means. Now, can we have worked without this? And the answer is no, we can actually not assume that a function is differentiable. It needs to be explicitly mentioned to us. So yes, it is necessary that they mention this to us. All right. The second little piece I want to talk about is what does it mean when they say selected values? Perhaps you saw it, perhaps you didn't, but it's important to go back and review this little piece right here, selected values, all right? And so if you looked at the tables, you'll notice that they've only got the data for 0 minutes, the data for 1 minute. So one may ask, well, then what happens in between 0 and 1, right? And when we say what happens, we mean how much coffee is there at like half a minute? How much coffee is there at 3/4 of a minute? And we don't know that. And because we don't know that, we understand that these are simply selected values, right? They've only given us selected values from 0 through 6. Now, the next question says is, how can we tell if there were exactly 7 ounces of coffee in the pot? So I think this is really where we have to start applying some of the theorems that we've learned, is can we tell if there were exactly 7 ounces of coffee in the pot? Now let me show you one simple way to do it, non-calculus based, just, understanding how to read a table really, all right? So take a look at this table. They're asking us, can we tell if C of t was ever equal to 7 ounces? Can we do that or can we not? Well, if you look at it very carefully, it goes from 0 ounces to 5.3 ounces to 8.8 ounces. Now, obviously it's a coffee maker. It's a liquid thing. And so in order for it to go from 5.3 to 8.8, it must have passed through 7 ounces. So between 1 and 2 minutes, it must have been 7 ounces somewhere there. See, I don't know exactly what that time is, but I know it must have been true. You understand? So how do you express this, right? How do you express this? Well, we're going to use the IVT in a moment, but first let's understand the structure, right? We know that at 1, the amount of coffee was 5.3 ounces. At time equal to 2 minutes, the amount of coffee was 8.8 ounces. So what that means is definitely between those 2 times, you know that there must have been coffee that was 7 ounces. So if you can understand that, you'll realize that the IVT is really what's being called here, because you've been given a function and you're being asked about when that function is equal to a certain number. That is how the IVT operates. They didn't ask for any derivatives. Okay, now let's practice the statement. The statement and writing the statement is very important, okay? So first thing that we do is we write down that since C of t is differentiable, all right, we know that it's differentiable, therefore it must also be continuous, all right? So we get that out of the way. Now, I know that this format tends to bother students a lot, so I'll focus on this again. First, you put the number that they're interested in the middle, right? And you put the inequality signs here and over here. And then 5.3 is the left end of the interval, right end is 8.8, meaning the values at those intervals, right, at those points. And so what we're saying is the C of 1 is equal to 5.3 and the C of 2 is equal to 8.8, right? So the number 7 falls between, therefore, the C of 1 and the C of 2. And so what we conclude is the IVT guarantees, notice how this has become a very generic statement, that there is some time between 1 and 2 where C of t is equal to 7. Now you might notice that in saying that statement in blue, it's easy to lose sight of how simple the question really was. All it was asking is, do you have enough to conclude that it must have been 7 ounces at some point? And in the past, if a student is able to explain this with the precondition in the more informal way, it'll be perfectly fine. But to have a formal method of writing and doing it, as I said earlier, is always going to be the better way out. And so learn the statement, right, and how it's written. Notice how we always start off with the precondition, right? And then after the precondition has been met, and we've mentioned it, then we talk about how that number falls between 2 other numbers, right? And then the third thing that we do is we say, therefore, the IVT is going to guarantee that there is some time between that interval. And then the fourth thing that we do is we write down that C of t is equal to 7, right? All right, now the next question says that can we tell the instantaneous rate of change at t is equal to 4.5, right? So instantaneous rate of change, what does that mean? That means an equation of a tangent line. It means the slope of a tangent line. And the problem is we don't really have an equation here, right? And we have been only given selected values, and even that is of C of t, We don't know anything about c derivative t at 4.5. And so the answer is no. We cannot tell the instantaneous rate of change, right? Because that would require an equation that we can take an exact derivative of. So then the question is, can we tell an average rate of change? And the answer is yes. Now, how do you tell an average rate of change? It's basically using the mean value theorem, right? That M stands for average, right? Mean. So how do you estimate exactly? Well, there is a specific way that you go about it, and I'd like to show you. So let's suppose that you were interested in the average rate of change at 4.5. So remember, it's a rate of change. So it's not asking you about how much, it's asking you about how fast, right? So how do you estimate when you don't have an equation or anything like that? Basically, if they're interested in anything between 4 and 5, and it happens to be right in the middle, 4.5, so you go between 4 and 5 because you know the number 4.5 falls in between closest to 4 and 5. And then you're going to use these matching up values to go ahead and set up a basically a slope, right? That's all it really is, right? Now, how is that going to look? Well, we're going to write down the equation. F derivative of c is equal to f of b minus f of a over b minus a, right? That's something that we know from before. But you need to be able to apply it to the context of the situation. So notice that the function was called c of t. And so if you want to say its derivative at some number, you would say c derivative at 4.5. And notice that this little equal sign means, right? That squiggly equal sign means that this is an estimate or an approximation. And then we can say f of b minus f of a is c of 5 minus c of 4 divided by 5 minus 4, right? And so if you take a look at the values that we have here, c of 5 is 13.8, c of 4 is 12.8. So 13.8 subtract 12.8 gives you 1, and then divide by 5 minus 4, that's also 1. So you end up with 1 ounce per minute. Now, notice how the units on the numerator are the units of c of t, and the units on the denominator are the units of t. So ounces per minute. Okay, the next question says, is there a time in the interval 2 to 4? All right, so in the interval 2 to 4, where you can tell that the derivative is equal to 2. Now, how do I know that this is going to be the MVT? Because given a function, they have asked me something about its derivative being equal to a number. Okay, so how do we go about this? Well, the question is asking if there's ever a time in the given interval when the coffee is falling as fast as 2 ounces per minute. All right. So in other words, they're saying, is the instantaneous rate of change ever equal to 2? That's essentially what they're trying to talk about. So what we need to do is we have to go back to our interval here. Okay, we have to spend a little bit of time on it to go back to our interval and look at from 2 to 4, right? Because that's the time that they were interested in. Look at 2 and look at 4. So at time 2, you have a y value or a c of t value of 8.8. And at 4, you have 12.8. So if you apply the mean value theorem in this situation, it's going to work out to your benefit, and you'll eventually get to an answer, right? But beyond that, what's important, and I've mentioned this several times now, is you have to mention the precondition. And it is so often forgotten by students. They really want to just get into the numbers, and they forget to write down that C is differentiable, therefore C is continuous, and then they go ahead and they show the mean value theorem. Okay, so C of 4 minus the C of 2 divided by 4 minus 2, as I just showed you, those numbers are 12.8 and 8.8 respectively, and so you end up with an answer of 2. So you go ahead and write out a concluding statement. You write down, therefore, by the mean value theorem, there is at least one time in the interval 2 to 4 where you know that the derivative is equal to 2. All right, Now, the last two examples that I want to do in this lesson is basically from the AP exam itself. So go ahead and pause this video and try example number 7 by yourself, and then I will go over it in a little bit. Okay, let's go ahead and try number 16. And again, it's important to just get used to the language that they're using. It says the function f is defined by this equation right here. The application of the mean value theorem. So this is rare, but they actually mention the MVT. All right, so when they're already mentioning it, it's a very good habit to just really quickly in the corner, just write down the mean value theorem. All right, so this is the mean value theorem. Like I said, it's simply an average rate of change, and you're setting it equal to an instantaneous rate of change. And they even use the value c there, right? So specific to our question, what we need to do is we need to take a derivative at c. Okay, we need to take a derivative at c, and that's all we essentially need to really worry about, is because it's not asking you what that value of c here is. What they're really telling you is if you did f derivative of c, and it's equal to f of 3 minus f of 1 over 3 minus 1. Look at how the question is structured. The question is simply asking what is that f derivative of c. They don't actually want you to find the point c. So in essence, it's actually easier than what we learned in the lesson, right? So what you need to do is you got to go back to this function here and find f of 3 and f of 1. So start with f of 1. When we try to find the f of 1, we end up with 2 minus 4 plus 1. And 2 minus 4 is negative 2, and negative 2 plus 1 is negative 1. So the f of 1 is negative 1. Now let's find the f of 3. The f of 3 is going to be 2 times 3 cubed minus 4 times 3 squared, and that is added to 1. So that becomes 2 times 27, which is 54. So that right there is 54. Then 4 times 9, which is 36, so minus 36, and then add 1. So 54 minus 36 is 18, and 18 plus 1 is 19. So we end up with 19 minus negative 1 over 3 minus 1, which is 4, which gives us 20 over 4, which gives us 5. So we know that f derivative of c is equal to 5. And that's all there really is to it. Oops, I just saw a mistake there. It's not divided by 4. I got crossed up between these and the minus and the negative right below it. But 3 minus 1 is actually 2. So 20 divided by 2 is going to give you 10. I noticed that when the answer choice didn't have a 5. So thank God that didn't have a 5. But there you go. The answer is going to be 10. So there's our correct answer choice. Okay, this next one you're going to need a calculator for. And again, I would highly recommend that you pause the video and you try this by yourself and then see how I do the question. All right, so the question says the function f is defined by f of x is equal to 3x minus 4 cosine 2x plus 1. And they give you its derivative as well. All right, so you've been given all those things. And again, they specifically use the words mean value theorem, right? So one of the first things that I'm going to do here is I'm going to just write down what the mean value theorem is. Okay, so very similar to the previous set is I write down the mean value theorem. Okay, now you want to take a look at the interval that they're specifically referring to. And so we know that the interval is negative 1 to 2. So I'm going from negative 1 to 2, and so accordingly I update a and b to be negative 1 and 2. Remember, they're put in the reverse order. It's f of b minus f of a. Now, we already know the derivative equation. I mean, you could have derived this yourself, but they're giving that to you. And so what you essentially need to do in your calculator is you need to evaluate what the function, which I've circled in blue for you, what the function is at negative 1 and 2. So here what I'm just really quickly doing is I am finding the function at 2. I am subtracting the function at negative 1. So basically using the mean value theorem, but just applying it in my calculator, right? So I end up with 3.34. So I know that there is some part of this derivative which is equal to 3.342186827. Now, how are we going to go about this? Basically, I'm going to go ahead and look for the intersection point between the derivative equation and this number 3.342 running, right? Because I'm trying to solve an equation, and an equation like this can be solved very easily in a calculator. I just need to find an intersection point, okay? So I'm going to type that number into my y1, all right? And I'll type in the derivative equation. Now be careful, I'm putting in the derivative equation, which I've circled in red for you, because I'm trying to find where the derivative is equal to this particular number, right? So I'm just going to kind of fix up the zoom here a little bit. And remember, I'm only interested on the interval -1 to 2, right? So I'm updating it for -1 to 2, and a little bit update on the y min and the y max. So take a look at where that intersection point is. It's possible that there's multiple intersection points. And so with the windows adjusted a little bit more, I find that the intersection points are going to be one that's negative and one that's actually very close to 1, right? And so using second calc and intersect, I look for those intersection points. Okay, and my first one is -0.478. And notice how there's only one answer choice that really has that. So if you wanted to go ahead and circle answer choice B and move on, you're welcome to do so. But to just be complete about it, what I'll do is I'll show you how to find the other intersection point, which is 1.049. Okay, and so the correct answer is the letter B. All right, so that does it for this practice, this example and this lesson. So you're going to have an assignment for this, and again, more details on this in class, but thank you for listening.